In the last lecture, we kind of went through the steps to derive the motion of equation for vehicles going forward. Okay, so that we ended up with equation number 2 here, which involves the mass times acceleration on the left-hand side, and the summation of forces on the right-hand side. So you have the traction force, you have the rolling resistance, you have the gravitational, and you have the air drag. Now this formula will be basis for a lot of calculations. If we know some of the values, we want to work out others. And also we can actually use this formula to derive some of the typical specification values for a car as well. So we're going to do both with some examples here. So, but remember this formula, okay? In the normal circumstances, you should really have to check what this formula is, okay? That really should be buried somewhere in your head. Next. Now, one of the things, if you have a car and you know how much output, the power output from the engine or the induction motor, you can actually work out one of the key performance indicators to say, given that motor, what is the maximum gradient this car or this vehicle can climb up to. Okay, so in this case, we can actually assume the vehicle is not accelerating. So it's actually, we are climbing up a gradient. So you probably will be asking for too much if you also want to have a high acceleration as well. So let's for time being assume it's not accelerating. It is moving very slowly up the hill. Therefore, the air drag you can ignore. Because it's also moving very slowly, we can actually ignore the rolling resistance as well. So in this formula, some terms will disappear because we are not accelerating. So MA disappears, so that's 0. Because we are not considering rolling resistances, so this term disappears as well. And because we are moving very slowly, and we're not considering the air drag as well. The interest here is to find out what is the maximum gradient it can climb up to in ideal condition. Okay, so no speed acceleration, no rolling resistance, and so on. So therefore, you only have two terms left. This is FTR, that's the traction force, and mg sine beta, that's the opposing force due to the gravity. Okay, and FTR minus mg sine beta. Therefore, and that equals to 0. Therefore, FTR equals mg sine beta. So we are saying that if there's no acceleration, if there's no air drag need to be considered, and let's assume the road surface is really in a good condition, what is the maximum curve we can apply it to? Now that is due to this force. This force comes from the engine or electric motor. So we know the mass. If you have a car, of course you should know how heavy that car is. We know this G, which is 9.81 or 10. Therefore, sine beta equals to FTR over mg. So that comes from the engine or the motor. This is the mass gravitational force of the car. So you can actually work out how much sine beta is. Or you can work out the beta, this angle of the gradient is. But typically, people don't refer a radiance to an angle or sine beta. What people normally do in a sort of civil engineering, they say, well, this gradient is 1 in 20 meters or 1 in 20. What does that mean? If you look at this triangle shape I have on the right hand side, 1 in 20 means the gradient going up by 1 meter, so A equals to 1, when the distance moved by 20, so B equals to 20. This is the horizontal distance, not the distance on the gradient. So it's really 1 in 20 means vertically going up by 1, horizontally going across by 20. Or sometimes people say, well, it's 5 in 100. That means 100, B equals 100, A equals to 5. So it's really that relationship. So the value people often quote for gradient is this value against that value. So it's A against B. Now, A over B is tangent beta. Okay? This is the right angle triangle between A and B. So we really need to convert this equation number 3 into the gradient, or the definition people often quote. So remember this formula, sine beta equals to FTR over mg. Okay, so I'm going to move to the next slide, and I'm going to copy this over. I'm going to define that maximum gradient, or the maximum gradability of a car, by gradient, which is tangent beta, and I can define that as a percentage. Tangent beta will give me a decimal point, but I can define that as a percentage. So if I multiply that tangent beta by 100, I get a percentage. Okay, either way, it really doesn't matter whether you use decimal point or you use a percentage, it's the same number. Now, when you look at this tangent beta and use what you did with trigonometry, okay, sine, cosine, tangent tangent relationship. Tangent angle equals to sine over cosine. So sine over cosine here in equation number 2. Now cosine square plus sine square equals to 1. Therefore cosine equals to square root 1 minus sine square. Now the reason why I'm doing this is because I know what sine beta is. Okay, now sine beta equals to FTR over mg. So I've actually converted tangent beta into the function of sine beta purely because I know what sine beta is. So substitute sine beta with FTR over mg in equation 3. Substitute this sine square with FTR mg square. This equation number 3 times 100 will give you the maximum gradability of a vehicle, what's the percentage of gradient, given the particular traction force, if we know the maximum traction force, and we know the mass of the car, or of the vehicle, then we can actually work out the maximum gradient the car can travel up to. Now, of course, there's a caveat to this calculation, because we are assuming there's enough friction between the tire and road on a gradient. So it could possibly be you have a very powerful engine or electric motor. It can give you a very high gradability. But the road is very slippery. It's like, in a winter condition, if you drive up a steep hill in a snowing condition, well, there's ice on the road, you probably have a quite high chance of the car slipping backwards. So bear that in mind, but we don't really sort of take this kind of extreme condition into consideration. And the maximum gradability is defined by assuming there's enough friction between the tire and the road surface so it doesn't slip backwards. Okay? And also, I've gone through all the steps to change from sine beta to tangent beta. The other thing that you need to notice is when the beta angle is very small, or the gradient ratio A over B is very small, tangent beta is very close to sine beta. Okay, so approximately sine beta equals to tangent beta when beta is very small or A over B is very small. In the range of sort of if the angle is less than 5 degrees, I'll be happy use the equate the two to get equate the two with the approximation. But when beta is high, as in this case, because we are trying to work on the maximum gradability, the beta can be quite high, so you can't use that approximation. So that's one of the things, or the vehicle performance indicators that we can use the motion of equation to work out. The second one is we actually work out what is the maximum cruising speed. Now, if you think about driving a car or a vehicle, you accelerate, you get the car into the speed you wanted, then you keep that speed, so you no longer accelerate. Now, in a normal circumstances, you would be a bit by the highway agent with the maximum speed you are allowed to travel. So the cars tend to have the traction force or traction power that is more than capable of going over the speed limit on a road. But let's assume we got no limit, like if we drive in Germany. Okay, if there is no speed limit, and what is the maximum speed we can actually achieve with a car? Now, of course, there are other safety issues. How good or competent a driver can be. But let's just put all these factors aside. Let's say, right, technically, from the power point of view, okay, from the traction power point of view, what is the maximum speed we can actually drive up to and keep the speed there? Now, if I go back to the equation there, the equation number 2 here, ma equals to all the forces together. To work out that, we are saying it drives to a high speed but keep the speed there. Therefore, when the speed is constant, so A would be equal to 0. Therefore, the left-hand side of equation number 2 would be 0. So I can actually move all the terms to one side. So these terms, when at a constant speed, all the resistance will be up against the traction force, i.e. the traction force is used to overcome the rolling resistances. The rolling resistance, the gravitational, and the air drag. Now, when we try to work out the maximum cruise speed, we can actually ignore the gradient as well. So we only have two terms. We can actually have only two terms here. But in this case, I'm actually putting the gradient in there as well, just in case we want to work out what is the maximum cruise speed on a gradient. So in the equation here, I have mg. If I put mg inside of this bracket, So mg times sine beta plus mg times fr cosine beta, and then plus last bit. So the first term here is due to gravitational force on a slope. The second part is due to the rolling resistance. The third part is due to the air drag. So the force here, so if we know the gradient, if we know the mass, if we know the friction rolling resistance, then we can actually, if we know the traction force as well, we can actually work out the maximum velocity that at cruising speed, no acceleration. Now this phenomenon can be explained using this diagram on the right hand side. On the right hand side, I have x-axis is the speed in kilometer per hour. The y-axis is the power of each running resistance, or power required to overcome in order to keep the cars or vehicle moving forward. Okay, so this straight line there is the power of the rolling resistance. Now, rolling resistance force is constant, but power equals to force times velocity. So as the velocity goes up, and the power goes up. Now this one, the second curve there, is due to the air drag. As you can see there, the force, air drag, the opposing force is proportional to v squared, and times that by another v to get the power. So you can see that the power of the air drag is going up really, really fast. Okay, in this case, we are on this diagram shows the power on a level ground. So beta equal to 0. So the gravitational force doesn't exist. You only have the second part. Cosine beta would equal to 1. Okay, so add the two power together, we get the third curve. Okay. Now, if you think about the characteristics of an electrical motor or the output from an engine, the ideal case, the power output for an engine or electrical motors for the ideal case is that, oops, it keeps going, is that you start from 0, the power will go up linearly, and then at some value, when you get to a certain speed, the power cannot be increased anymore, so it goes flat over. Okay, so for a particular engine or electrical motor, it is a cross point with the final curve here, and if you go down, this will be your maximum cruising speed. But we have this formula. We don't really need. I'm just using this diagram to explain the principle behind the maximum cruising speed. Okay, but this equation itself is sufficient for our calculations, so we can use this to calculate the maximum speed for when the vehicle is cruising and overcome all the running resistances. Okay, so three things here. One is the first equation, the final motion of the equation. If we use this derived, how to calculate the maximum gradability, the maximum gradient the vehicle can climb up to. We can also use this to work out the maximum cruising speed, no acceleration anymore, cruising speed of a vehicle, which tend to be higher than speed limit on a particular road. Otherwise, nobody will buy your car. So if your car is not capable of going up to that speed beyond the speed limit on the road, then people won't be happy. So you need really sort of part of design is to make sure that your car is capable to output the power and the traction force to go to a speed beyond the speed limit. I'm going to use this example to show how the calculations can be done and how we can actually work out different values. Okay, so I have an example here. Says a series HEV has a mass of 1200 kilograms. The maximum traction force for the motor is 1.5 kilonewton. That is converted to the force already, not the torque. Okay, sometimes you might get a definition of a torque, in which case you would have to convert to a force first. Okay, but I'm giving you the force straight away. So what kind of performance parameters can be derived from here? A lot. For example, we can work out the maximum gradability. In this case, I know FTR is 1.5 kilonewton. I know the mass, so it's a straightforward calculation, but make sure you use the standard SI unit in all calculations. Okay, so the mass, the standard SI unit is 1200, so I'm going to put M here. I'm going to put 1200 here. G equals to 10 or 9.81. Yeah, my mouse is really sensitive here. And FTR is 1.5 kilonewton. The standard SI unit is Newton. So we need to convert this into Newton. So 1.5 is 1500. So FTR is 1500, FTR is 1500. This 100 there, as I explained before, is just indicates a percentage. Do all the calculations. I'm sure you are more than capable of. And it works out 12.6%. Okay, it's quite, fairly steep gradient, but not extremely high. So it's basically saying it goes up by 1 meter over 12 points for every 12.6 meters. We can also work out the maximum acceleration as you just start the car on a level ground. So there's nothing else. So I'm not talking about the rolling resistances. In our ideal case, on a level ground, there's no air drag, there's no rolling resistance. What is the maximum acceleration you can get out of it? So that's just ignore all the rolling resistances, and therefore FTR equals MA. I've got rid of all the other forces on this side. Okay, therefore A equals to FTR over M. That's really sort of ideal, absolute maximum acceleration you can get out of this car. So it's 1500 divided by 1200. That's give you 1.25 meter per second square. Now, if you want to avoid mistakes, it's always useful to stick the unit of your calculations at the end, so there's no mixed up. Especially when we get to the stage when we consider the rotational velocities, that kind of stuff. Sometimes they're defined in radians per second. Sometimes they define as revolution per minute, that kind of stuff. So make sure you get them into the right unit. The speed of the vehicle is also can be defined in meter per second. That's a standard SI unit. But also sometimes people define it as kilometer per hour or miles per hour. But standard SI unit for speed is meter per second. Okay, so always stick with the standard SI unit, then you are less likely to make mistakes or mistakes that shouldn't have made. So what else can we do? We can also work out the maximum acceleration from a standstill on a gradient. in the previous calculations, we did calculate the maximum acceleration available on a level ground. There's no gradient. Maximum acceleration or gradient. Now, again, I'm going to ignore the rolling resistance, assuming ideal case. I'm going to ignore the air drag because we are starting to accelerate. There's no speed yet. So the only opposing force opposed to the traction effort is mg times sine beta. Let's say the gradient is 3%. Now it's small enough, so tangent theta is approximately the same as the tangent beta is approximately the same as sine beta. So I'm actually, this 3% is tangent beta. So I'm going to use this 0.03% for the sine beta as well because it is close enough. Okay, so A equals to total traction force minus mg times sine beta. Beta is the gradient angle. Because sine beta and the tangent beta is approximately the same, and the tangent beta is equal to 0.03 or 3%, therefore approximately sine beta equal to 0.03. The total force is 1500, traction force. M is 1200, G is 10, sine beta is approximately 0.03, divided by M, I get 0.95 meter per second square. So on level ground, we would be able to achieve an acceleration of 1.25 meter per second square. But even for a small gradient like 3%, 0.03, it's pretty small. The acceleration goes down by quite a lot. Okay? Reduced from 1.25 to 9.5. So all the factors affect. So if we have to include the consideration for the rolling resistance as well, then this maximum acceleration will go down further. But you need to just include that force in there as well. If you accelerate at a higher speed where air drag needs to be included, then of course the performance will be even less. We can use use the calculation for other things as well. Now let's assume a vehicle is climb up the gradient of 0.03 or 3%, and it has an acceleration of 0.95. But what I want to find out is how much this velocity or what is the speed it can achieve after a certain time. It's another parameter people often quote in a car for performance. Say, how fast can you accelerate? And in 10 seconds or in 6 seconds, you get to 100 km per hour or that kind of stuff. So let's say in 10 seconds, I want to find out what is the speed the car can achieve from standstill. So in this case, the formula to apply, this is what I asked you to revise before. V equals to A times T, because A is a constant, plus V naught. Now I put a V naught there because V naught is the initial speed before that you start to accelerate, at the beginning of acceleration. But in this case, we are saying it is at standstill, so V naught equal to 0. So A is 0.95 times T is 10. So therefore, in 10 seconds, the vehicle speed would be 9.5 meters per second square. You can convert that to kilometer per hour or miles per hour if required. Okay, but that meter per second, 9.5 meters per second, that's the speed in the standard SI unit. We can also work out how far it has traveled in 10 seconds. S, in this case, the formula is S equal to half of A times T squared. A is a constant. V naught is the initial speed times T. Now V naught equal to 0, so this second term doesn't exist for this particular calculation. So it's half times A times T squared. A is 0.95 times T is 10 seconds, so that's times 10 squared divided by 2. And we end up with 47.5 meters. So it's not very far. 10 seconds, you travel just less than 50 meters. And you can also work out the acceleration if there are different running resistances that need to be considered. So in the previous cases, I did calculate the ideal case when there's no maximum. There's no running resistance at all. Or in the second case, I will show you how to calculate the acceleration when it's on a gradient. But you can include other factors if you know them as well. Okay, the formula is the same. Okay, ma equals to all the forces. So that is rolling resistance. That's gravitational due to on gradient. This is air drag. Okay, the formula is there to apply. You can actually use this formula to work out the maximum cruising speed as well. Now, when we're talking about cruising, that word means no acceleration. Okay, so A equals to 0. And you can actually derive from there, if A equals to 0, the total force must equal to all the resistances. And therefore, if I move this term to the left-hand side, divide by the coefficient of V squared, that's all that, do a square root, that will give me V. So if we know the traction force, we know the rolling resistance coefficient, we know the mass, we know the gradient, and we know all the parameters that relate to the air drag, then we can actually work out the maximum cruising speed using equation number 3. Okay, so that's my example, and I think that, yes, that's okay. Now we are come to the point where you can practice. Okay, I'll set this question up for you. It's fairly straightforward, all the calculations, and nothing beyond what I have introduced, including my examples. Okay, so you should use your tutorial time to practice, if necessary, at another time as well. But it's better just to keep to the timetable to say, right, I have 3 hours, but I've watched all the videos. I still have more time, so I might as well use this time to do the practical questions. Okay, I'll see you next time. Thank you.